Okay, so our final talk in this session will be on efficient induction of language models via probabilistic concept formation.
All right, can you hear and see my screen?
Yes.
Okay, great. Hi, everybody. My name is Chris Maclellan. This is work that was conducted with Peter Matsakis and Pat Langley. Oops. So sort of the basis for this idea is in 2013, there was some influential work on a system called WordDevec, which generated that one can extract meaningful semantic information in the form of word embeddings from analyzing words in their surrounding context. And this early work, which was, I think very seminal in that it grew later into a lot of the language modeling approaches that we see today, such as BERT or GPT, like we were just hearing about in the last talk. And many people think that these language models have, in some ways, a lot of potential to transform different aspects of society. I mean, these models have a lot of applications. But despite all this excitement, there are a number of limitations of these current modeling approaches. So first, they require substantial data and compute to build. GPT requires internet scale data. And I think there's some quotes that estimate it takes something like $12 million to train the GPT model. Second, mainstream systems are inefficient in their ability to update when new data becomes available. So typically these systems train in batch and they experience things like catastrophic forgetting. So what that means is that when you get new data, you often need to retrain on the new data plus all the old data that you had. So you have to basically, retrain, spend another 12 million in compute in order to build another model with some new data being incorporated into it. Now, the reviewers of our paper actually raised a great point about how these models are used, where they take the pre-trained large language models and then they'll fine-tune them for particular domains. So I think the idea here is to try to capture some of the cost that's been invested in these models and use the pre-trained models in order to improve performance on a target task. But there's actually still a number of issues that come up when you're trying to do this. So they still often require a large amount of target domain data in order to build a model for the particular thing you're doing. And they can still experience catastrophic forgetting. So if you're repeatedly fine-tuning the model, say as new data is constantly coming in, then eventually you start to forget some of the things that were part of the original pre-training, if you're not including that data in the training of the model. And there's also some recent work that we came across, which actually suggests that very little knowledge is actually transferring from the pre-trained models. They have some interesting results showing that if you pre-train and fine-tune on the same target domain data, you can do almost as well as if you take like one of these large pre-trained models and then fine-tune it for your domain. So actually suggesting that maybe it's not that there's something transferring from the pre-trained models, it's actually something about the pre-training process itself, which is what's benefiting some of the work that's been coming out lately. So in our approach, we aim to try to overcome some of these limitations by taking building a new class of language modeling approaches that adhere to Langley's constraints on human learning. So really, our goal is to build systems that acquire modular structures in a piecemeal and incremental way that builds on prior knowledge to guide learning. And the end result of that is we hope to be able to acquire expertise rapidly with reasonably few examples. So as a basis for our approach, we're using a system called Cobweb. And Cobweb is a concept formation system that's based on psychological studies of how people form concepts. And this system emphasizes the incremental nature of learning. And it has some unique abilities, like the ability to adapt its conceptual structure to reflect new experiences. So in many ways, I'm not going to go into the exact details of how it does it, but it addresses each of these constraints on human-like learning that we're interested in. And there are many variants of Cobweb out there right now, ones that support different aspects of different kinds of tasks and different kinds of characteristics of the input. But none of those existing implementations, they don't explore learning a language model from sequential text input. So that's really the focus of our work here, is to try to create a new variant that can support language modeling. So before presenting our new systems, let me first explain how this original Cobweb system works. So instances in Cobweb are represented using an attribute value representation, and concepts are stored in they store a table of attribute values along with probabilities based on how likely these attribute values are to occur in instances that are covered by the concept. So in this example on the left here, I'm showing an example of a red square. And on the right is a Cobweb concept hierarchy that initially is just empty. So this is our first example. So given that we have an empty tree, the first thing that we do is we update the concepts, the root concept, to reflect our first instance that comes in. Next, we get another instance, in this case, a green square. Now that the tree already contains a concept, instead of just updating this node, we actually, whenever we have a leaf node, we fork the leaf node. So we keep the original concept that we had, we create a new concept to represent our new instance, and then we create a new merge of these two that represents both of the concepts that are stored underneath it. And you can see here that I updated the probabilities. So the two leaves here have basically 100% probability of each of the attribute values. They almost representing a single instance. And then our intermediate node here has these, 1/2, and 2 out of 2, representing the distribution of the attribute values over all the examples we've seen so far. So now we get a third example. In this case, it's a green circle. So in this case, we start by adding the instance to the root concept because it's not a leaf node. So we just update the counts. Then we consider how to add it to one of the children concepts underneath the current node. Now, in this case, we decide to add the example to the green square because they share the same color. So now we're again adding to a terminal node or a leaf node. And in this case, we're going to fork it again, create another concept to represent our new instance, and then a merger of those two. So this just kind of gives you a flavor of how we're incrementally constructing our concept hierarchy as new examples are coming in the original Cobweb approach. So at each node in the categorization process during learning time, Cobweb considers 4 update operations, which I've shown here. So it considers adding the instance to one of the children, the existing children. It considers creating a new child. It considers merging 2 of the children and adding to the merged node. And it considers splitting one of the nodes and promoting the children and then repeating the process at the current node. And in each of these operations, it chooses which one to do using a measure called category utility, which is, you could effectively think of it as like the mutual information. It's trying to maximize the mutual information of the children. And at performance time, Cobweb only considers a subset of these. So it only considers adding and creating. It's basically just sorting down the tree and not updating the structure or the weights, the parameter values, the probabilities. It sorts down the tree, and then when it reaches some type of node, either where it's a leaf node or an intermediate node where it thinks it's best to create a new child, it will stop, return that concept, and that concept can then be used to make predictions about the instance. So the Word2Vec work that I was talking about earlier introduced a couple of interesting ideas for analyzing words in their context. They actually introduced 2 different approaches. One of them is called the contextual bag of words, or CBAW. And this approach learns an embedding that supports prediction of an anchor word given the context. So you could think of it as when you're training the model, you're basically taking all the context words, learning and embedding representations for each of those words that when you sum them together, you can use that sum to predict the anchor word. The skipgram model does the reverse of this. So it takes the anchor word and it tries to learn an embedding of that that can predict all of the context words, which words will appear within the context. So we took these ideas, these CBAW and skipgram ideas, and we tried to incorporate some of the insights from Word2Vec into the Cobweb system. And to do that, we created three variants of Cobweb: the word system, the leaf system, and the path system. Now, the word system combines Word2Vec ideas. I would say it's the most direct translation of these ideas into Cobweb's probabilistic concept hierarchy framework. And then the leaf and path system, they both introduce more sophisticated ways to account for context during performance and learning. So let's go through each of these examples of these systems. So first, let's talk about the Cobweb word system. So similar to Word2Vec, we chose to represent each instance in terms of an anchor. That's the anchor word and its surrounding context. So here's an example of a sentence from Sir Arthur Conan Doyle's Sherlock Holmes stories, along with an instance for our word system that's based on this text. So in this case, inspector is our anchor word. and we have a context window of 4 words before and after the anchor. So as the instance description shows, we actually, in the word system, what we're doing is we're extending the original Cobweb representation, which normally would have just been attribute and value. But now we extend it to also include a probability distribution over each of the attributes. So anchor in this case is 1 out of 1 because there's only one anchor word. But our context, we actually have a probability distribution representing how likely these words are to appear in the context. So you can see the word the appears 3 times in the context. So 3 out of 8 here is what we store in our instance description. And then we've updated the Cobweb algorithm is pretty much the same. We just made a minor change where we update the way that we keep track of the counts in the concepts that store this instance. So this here on the right now is a concept that's storing this instance and one other one. And we can see that, there's 2 anchor words, inspector and police. They have a 50-50 probability. And then the context, though, you can see how here the denominator is out of 16 because there's 8 context words in each of the 2 instances that we've seen so far. So what we're doing with this approach is we're actually learning a joint distribution over both the anchor and the context. So, CBOW was trying to predict the anchor given the context. The skipgram was trying to predict the context given the anchor. And here we're trying to learn a representation that being able to predict either the anchor or the context. So we're basically combining the 2 approaches together into a single model. So a major insight of the word2vec model is this idea that words are represented by their embeddings rather than by the specific words. So in the word system I was just showing you, we actually represent each of the words by the word symbol, like the string itself. So we're not really taking into account this insight of having some embedding or other representation of the word. So the Cobweb leaf system aims to try to incorporate this insight into our first variant, the word system. So let me show you how this works. So this approach actually takes an iterative approach to building up the instance representation. So here's that same sentence that I was showing before. And now I'm just showing here, I'll kind of show in this example following along, we have an existing concept hierarchy. So we have an existing knowledge that we're using. So first, it creates an instance for each of the words that appear in the context window. Now, and what we do at first is we create the instance for each of these words where the instance contains the anchor and no context elements. So we're just using the sort of first pass here. We just use the anchor words themselves. Then what we do is we sort this example down our concept hierarchy until we reach some type of a terminal node. And in this case, we actually take it all the way to a leaf node. And we categorize this example in a non-modifying way. So we're not updating the weights or the structure of the concept hierarchy as we're incorporating the example. And additionally, since we limit it right now, we don't have any context elements, just the anchor. We actually restrict it to paths that contain the target word. So we're really guaranteeing that we end up with a concept that's somehow representing this word. And in this case, if you look at the little concept hierarchy in the bottom right, we can see that we categorize it as concept 12, and we attach this concept 12 label to the word. Then we move on to the next word. And in this case, it's house. We create an instance for that. We sort it into our concept hierarchy, get a concept label, and attach that to the word. And this process continues for all the words within the context window. So we attach a label to each of the words. Now we actually repeat the process again. We start over at the word the again. And now we construct an instance to represent this word that includes context elements that are based on the concept labels that we generated on the first pass. So now we have the word the, but now we have some context around it that's being described not by the words themselves, but by the concepts that are representing those words. So in this case, since we're at the edge of the window, we only have 4 concept elements that appear within the window. So we have concept 55, 17, 12, and 99. We sort it down the tree. And in this case, we end up at concept 12. So actually the label for the word doesn't change, but it might, depending on the context. So maybe here in house, we create another instance using the concepts around it as the context. We sort it down the tree, and maybe now the concept is just slightly different than it was before. Now it's concept 400. So we would update that label for the word house. And this process would continue. And we update all the labels based on now including the contextual information. And we actually repeat this process we could repeat this process until convergence. We actually do a finite number of iterations. So I think we do 3 iterations in our approach. So we just do 3 passes to try to get the model to converge to a stable representation that includes the contextual, the concept labels in describing the context of the anchor word. Now, once we have this, we take our target word, the anchor word, inspector in this case, and we create a new instance now that includes the context, which is described by the concepts in our tree. And then we just do what we did before with the Cobweb word model and with the original version of Cobweb, where we would incorporate this instance into our tree in a modifying way, and we would restructure the tree and update the weights as we incorporate it. So one interesting thing to note here is that in Word2Vec actually maps each word to a single point in an embedding space. And ironically, that actually makes it impossible to represent homonyms. So different variations, like the same word, but different meanings depending on the context. Now here, because we're creating these instances that describe the word and its context, we can actually learn different versions of inspector, for example. And we'll talk a little bit more about that in just a second. So now, one challenge with the leaf system is that it's only using labels from the terminal nodes of the concept hierarchy. So we made this decision because the non-terminal nodes, the intermediate nodes in the hierarchy, are constantly getting restructured or deleted. And as a result, they tend to provide an unstable representation for learning because they're constantly changing. But what we found is that the leaf system, even though we're using these leaves and the leaves, they never get deleted or restructured, or they might get moved around, but the leaves never get deleted. One of the problems, though, is that we found that we still create too many leaf concepts to represent a single word. So, like the word inspector, maybe every time we see inspector, we actually form a new leaf. And when we're categorizing each of these words, sometimes we find that, it's somewhat arbitrary which exact leaf we end up in. And this produces the context elements where the concept labels are changing, makes it difficult for us to learn a stable representation. So we've employed a couple of tricks where we actually, in the leaf system, we would find that if there were multiple leaves that were next to each other that had the same, that were representing the same anchor word, we would actually just group them together. So we tried to combat some of this, like splitting of the, this explosion of the number of concepts we have that represent the same word. Another way that we've tried to overcome it is with this path system. So the path system actually doesn't look just at the leaf itself, but it looks at the entire path along the way. So let me show you what that looks like. So here's our sentence that we had before. Now in the leaf model, we would represent each of the words by using the terminal concept that represents it. So the leaf of the path and the concept hierarchy. Here, we're actually going to instead represent it by all of the concepts along the path. So we're going to represent it, attach to it the label for concept 1, concept 8, and concept 400 in this example. So then what we do is we apply this actually to sort of the same approach we were doing with the leaf model, but now we track all of the concepts along the paths, not just the terminal concept labels. We then build up an instance representation, similar to the leaf approach that includes all of these labels. So in this example I'm showing here, I'm actually just showing the context elements for the word house. So we see we have concept 1, concept 8, and concept 400. And one interesting thing to note here is that the root concept, concept 1, actually appears in all of the words. So we would say that we would have 8 out of 8. So we have 100% probability that that concept appears in the context. Similarly, concept 8, is some intermediate label, and that maybe is shared by some of the words in the context. Maybe 3 out of the 8 words share that. And then concept 400, the leaf concept for the word house, maybe only appears once, so it's 1 out of 8. And we have this sort of description for all of the words in our context. So notice, though, that this will create a lot more entries in our instance representation. And another thing to note here is that the sum of the probabilities for all the context values no longer sums to 1, right? Because concept 1 here has 1, and then concept 8 3/8 it'd be more than 1. So we don't actually have a valid probability distribution over the context values. But I'll get back to how we deal with that in a second. And then also, we mentioned previously that the intermediate nodes of our concept hierarchy are constantly getting restructured. So we actually had to come up with some new mechanisms for tracking when a concept gets deleted or a new concept gets created. And we dynamically update all the nodes in the concept tree that refer to that concept that's getting restructured. So like if we deleted say concept 8 here, we would go and find every node in the concept tree that refers to concept 8, and we would remove concept 8 from its table. And we have a way of doing that with effectively like pointers between the different concepts in the tree. So we keep track of all the nodes that refer to or do anything with concept 8 so that we can update them efficiently. So I was mentioning that we no longer our values produce a valid probability distribution. So to deal with that, we actually updated the category utility equation to account for all the concept labels in the path that we're tracking. So category utility is computed over a decomposition of a concept into its children concepts. And it's basically measuring how many attribute values we could correctly guess in the children over the parents. So what's the increase in the number of correct guesses that we can make. So the way that this works here is I'm showing the original expected correct guesses equation in the middle. So there's this idea that like what's the probability that we correctly guess the anchor? And what's the probability that we would correctly guess the context elements? That's the two terms there. In the leaf and word systems, we use the original formula for computing the anchor. That's the term on the left here. But we update the way in which we compute the context elements to basically say we're computing what's the probability that any given concept appears in the context or not. So it's almost like a multi-label prediction reformulation of the category utility score. So we have a way of dealing with this so that we can now take into account all the information in the path in a way that what we're basically looking at is what's the probability of the particular anchor word, and what's the probability that any given concept appears in the context or not. So given these three approaches, the word, the leaf, and the path system, we conducted some preliminary evaluations using the Microsoft Sentence Completion Challenge dataset, which contains a little bit over 1,000 sentences extracted from Sir Arthur Conan Doyle's Sherlock Holmes stories. And we conducted 3 evaluations: a synonym grouping test, a homonym grouping test, and a synonym recall test. And then we also conducted an asymptotic analysis of the runtime of our approaches. So to evaluate how well our system does at putting synonyms close together, we sampled 200 sentences from the challenge data set. We identified the 5 most frequent words after excluding stop words. We copied all of 200 sentences 5 times, and in each of the variations, we would replace the most frequent words with the word with an index attached to it. So, every occurrence of the word door, we would copy the sentence 5 times, and each of the variations, each of the 5 sentences with the door would be door 1, door 2, door 3, up to door 5. So the idea here is that this ensures that we have 5 different words, 5 different variations of door that all have identical context. So they're basically synonyms of each other. So we trained the system using these sentences, and we evaluated whether or not the system grouped the synonyms together. And we did this using a measure called the adjusted RAND index. So we use the ground truth label. We know that all 5 door variants are the base word door. So we look at how well our system does at putting all the door variants together. And what we found is that in this case, the word system actually does the best. The path system does, it does okay. Both the word and path system do better than chance at grouping these. So they're like grouping them closer together. And the leaf system, unfortunately, seems to be doing just about chance performance on this. So next we look at homonyms. So the homonym grouping task used a similar process to generating our data. So we took 200 sentences, we found the 5 most frequent words, we copied the sentences 5 times. But here, instead of replacing the most frequent word with an indexed variant, we actually replace all the words around it. So if we have the sentence, I like cats, it would become, I-1, like-1, and cats. So we would replace all the words around cats with the index variant. And what this does is it basically gives us sentences where now we have these words like cat, cats, that it's the same word, but the context is always different between them. So they have completely different contexts. So we trained our system using these sentences, and then we looked at whether or not how well our system does at separating the different homonyms from each other. And in this case, we found that the path system actually does a really good job at separating the homonyms. So it does perfectly separates them. The word system does better than chance. And the leaf system, in this case, is just giving us around chance performance. So our third evaluation looked at the ability to map incoming instances to concepts that describe the anchor word or one of its synonyms. So here we apply an iterative approach, or sorry, not an iterative approach. We apply an approach similar to the synonym recall test. We actually sampled 400 sentences in this case, so more sentences. We copied the sentences 50 times, or sorry, we took the 50 most frequent words, we copied the sentences 5 times, and we replaced each of the most frequent words with their variants. So it's like the synonym test. We have words that are different, but their context is the same. And then what we did is we just incrementally trained. I'm sorry?
All right, about 5 minutes left. Sorry.
Okay, thank you. Yeah, so we trained our system using these sentences, and what we did is we looked at how well they're able to place those instances into a concept that predicts either the anchor word or one of its synonyms. And we also we wanted to evaluate how well this would compare to a word-to-vec approach. So we created a similar model here that trains on all the sentences up to a given sentence, and then it tries to predict the anchor word or one of its synonyms using the context elements. So what we found here is that the path system actually does the best. It very quickly builds a representation where it can map the incoming instances to concepts that describe the anchor or one of its synonyms. The word system actually did surprisingly well. We were kind of surprised how well that system is able to do, even though it doesn't have like an embedding representation. You know, it's just using the words directly. It doesn't have any kind of intermediate representation of the words. And then the leaf system and the word-to-vec system actually do the worst, and they have similar performance. And those are the two that are shown at the bottom here. So lastly, we conducted an asymptotic analysis of our approaches. And we found here that the word system had the most efficient runtime. It's basically n log n, where n is the size of the training set. And the remaining systems have roughly comparable performance. So the word-to-vec and the leaf systems and the path systems have roughly n squared log n performance. Now, this being said, our analysis shows runtime for all of the training data. So we're training on all the data at once. But the word, leaf, and path systems can actually do incremental updating. So if we get a new data point, we can update them in log n time. Whereas, log n for the word model and log n for the leaf and path models. And in contrast, the word-to-vec system would have to retrain on all the data, including the new data points. So it would be n squared log n. And this, I think, really highlights sort of the efficiency of our approach, is this ability to incrementally update our knowledge as new examples are coming in without having to retrain on all the data. So in conclusion, our work provides some preliminary evidence for a new approach for efficiently inducing language models. And the path and word approaches show some promise in terms of synonym and homonym grouping. They do substantially better than chance. The path system makes the most rapid progress on that synonym recall test, which we think is due to the system's ability to adjust its representation. It's using these, the intermediate representation of words, and it's taking into account the entire path information. The word system does reasonably well on the synonym recall test, and the leaf and word-to-vec systems have reasonably low performance at least for the amount of training data that we're using here. The asymptotic analysis shows that our approaches are at least as efficient as word-to-vec, which is widely viewed as a pretty efficient approach. And our approaches support incremental learning and reasoning about homonyms, which word-to-vec doesn't do. Just looking forward into the future, the word variant did better than we expected. So we actually think it's worth exploring some variations of that approach. We'd like to investigate the leaf system a little bit more. It's currently has pretty low performance. It's using just a single concept description. We'd like to explore the idea of dynamically choosing some intermediate representation for the words. The path approach offers a novel method for dynamically updating the underlying representation during learning. So we want to explore that some more. We believe this current work, though, sets a stage for new approaches for doing language modeling that differ considerably from the current language inducers that are out there, like Word2Vec, or even the more modern stuff like GPT. So for example, we think that there are ideas here that could be translated into other systems. So SME or SAGE, for example, which we heard about just the other day, we could maybe incorporate some of the ideas we're talking about here into a model like that to do incremental language modeling as well. And so lastly, we're investigating how we might apply these approaches to some of the standard language modeling benchmarks now that we have these basic systems. So I will end there. Thank you.
So I guess we have time for a very, very quick question. There's basically 1 minute left in the session. Does anybody have anything super quick? Okay, so Chris, I will say there is a detailed question from David on Slack, so I would encourage you to follow up with him on the Slack channel on that.
Great.
Quick follow-up, Chris. This is Pat.
Yeah.
So I think it's worth pointing out that although we were using context in the same way that Word2Vec does, just the surrounding words, it's not limited to that. We could use other senses of context, like the results of a parse tree, or some background knowledge in a semantic network. Those could be used as context too, and our approach should work for that.
Yeah, absolutely. And there are variants of Cobweb that support the ability to handle structured and relational information. So, we could imagine having systems that take into account other relational information that we have as context.
Okay, let's thank our speaker again.